intelligence. Turing back in 1950 defined it as mimicking human intelligence in computers, and it's pretty obvious. Now, taking a step further, okay, how does that differ? How does artificial intelligence differ from traditional computing? Because traditional computing is mimicking human intelligence computers. It's taking stuff that we do, our thought processes, and automating them. That's is that artificial intelligence? Probably back at that time, it was considered that because we were, doing things with computers that people had to do, calculations, all that kind of thing, data, storage. It's traditional computing, but it's not really artificial intelligence, not the way we think of it today. Traditional computing was transactional, and well, still is, I should say. It's kind of like software 1.0, this traditional computing, and I should have put it this way. But as everything, you did everything in one step at a time. You wrote an algorithm, and that algorithm was your process, and each process had a different algorithm. So you defined what your procedure was, your process. You talked with the business. You looked at nature. You said, okay, this is how things work. I'm going to write a program to mimic that, and very distinct code for each one. And everything, in that case, all your data it's everything stored with ones or zeros, on or off. Discrete mathematics. So artificial intelligence, the way we think of it these days, is more like taking a look at the brain. How does the brain work? Our physical brain. And, how do we do things better than computers? Computers may do things faster, but we are able to do many, many things better. Why can we do that? So looking at breaking apart how the way we work and copy that in hardware. So what are the things about us that's different? We do things with a very massively parallel, very simple processor, the neuron. Everything is analog. It's not digital, on or off. There's definitely digital aspects to it. The output of a neuron is either like on or off, excited or not. And that's a key part of the communication between neurons. But it's still an analog process. It's chemicals. It is electricity, but it's not these transistors that are just the output is on or off. It's sending out a signal. And also in traditional computing, your output is either right or wrong. Everything is 1 or 0. Everything is distinct. Whereas the way our brain works is, we're imperfect. We have this, we can estimate things, we can guess. And even though we're not right all the time, we're still darn good. We don't have to be, because there's this 80-20 rule or 99-1 rule, where as long as you're very, very close, you're good enough. And so if we develop this in hardware and in a robot or something, in a computer, and it's not right all the time, is that okay? Is that good enough? And many people don't think that it is. Like for instance, that car accident down in Arizona, in Phoenix, Uber car that hit somebody on a bike. Just because that was an automated car, if it was a driver, if it was a computer, it should be perfect. That's the expectation. But it won't, and it will never be. and it's not supposed to be. That's not the way we do neural networks. That's not the way we work. We're trying to copy that. It's just that if it's 99.99% right and wrong, 1 out of 10,000, is that okay? That's the goal. And as we go along, we're going to see that's where we're going with this is we're trying to get 99% right with estimates. And then if that's good enough, if it's there, then we've succeeded. Because otherwise, it just would not have happened. Too complicated to develop this with traditional computing. We can do so much more, and the key is the common architecture. I mean, if we do everything with neural networks, if we solve all of these problems with that's made up of neurons, and they're all the same, and so we're solving a problem with a vision problem, NLP, language, listening, or a retail problem, trying to predict something, supply chain problem, all with the same code, the same program, just a different set of data coming to train it with, and some tuning, some understanding of how neural networks work, how big they should be, maybe, but it's all the same code, and you're just applying some trial and error to it to see how you can configure it, some configurations. So that might be the most amazing part of this. Yes, I will be covering time series forecasting. Yes, absolutely. That's one of the most amazing things. And I think we'll talk about that some. Okay, so we kind of talked about this a little bit, periods of artificial intelligence. Early artificial intelligence kind of happened from, it had its boom in the 70s up through, early 90s, then kind of died off and picked back up in 2005 and became what it is today. Hinton kind of got things going again in 2005 with his stuff on CNNs, which we're going to go through that. We're going to see his stuff. We're going to write programs. Everybody's going to be doing it themselves. And it's a big network. It's not small. But we'll see the results. Everybody will have it on their own computer. Data scientist, that term really didn't exist before 2008. DJ Patel, who was under our last administration, our chief data scientist, and Hammerbacher back in 2008, who was at Facebook, coined that term data scientist. That really kind of took off at that time. That's when people were being hired as data scientists. It wasn't until then. Before that, it was data analytics, perhaps. Yes, we'll be doing CNN from scratch. We'll be developing it up from scratch. It's not that complicated. Okay, so we kind of covered all this already. So here's a graphic of deep learning. Actually, this is artificial intelligence, I would say, building up deep learning. Neural networks, the very first neural nets were talked about in 1943. A model of how the neuron works was developed back then. You had a perceptron right off the bat, which is just one neuron, and that was defined. A few neurons together does the XOR problem, which we will be doing the XOR problem sooner than later. And at that point, they didn't know how to train the neural networks yet. They had just figured out how to use them, how to configure them, train them manually. Then they came up with backpropagation, a learning And then now we have learning, an iterative process of, positive reinforcement, actually negative reinforcement, trying to minimize an error. So moving along, multi-layer perceptron is, that's, I don't the difference between that and backpropagation, you're basically just having more neurons with that one. And then recursive neural nets came around that time, RNNs, which is a neural network that has an idea of the time state. Looks like LSTMs came along that time, long short-term memory neural networks. And we'll be developing these. We'll be looking at how these came about. And then new stuff, dropout is a big thing. New way that neural nets could be faster. So yeah, this is kind of give you an idea of how long ago we started doing this. I mean, computers really didn't come out till in like the 1950s with transistors. So neural networks have been around since computers got started. All right, so a little bit of history about the AI concepts. Early forms of artificial intelligence, fuzzy logic, genetic algorithms, and the statistical methods. You can consider statistical methods to be AI because it's learning. The way you come up with statistical methods, you can develop them by the learning algorithms, where they iteratively get the answer. Then neural networks. That's a more recent excitement. But as I showed in the previous slide, it goes all the way back. Perceptrons, backpropagation. We went through this. There's a couple of links here that are very interesting to look at on where how AI came about. I strongly suggest going back and looking at that. Okay, so the difference between artificial intelligence and machine learning. They're really very, very similar concepts, looking at them from a definition. We have an intelligence, something that's smart, that's not real, so it's artificial. It's not human. But machine learning sounds a lot more techy and a lot less kind of scary. Artificial, that means it's not human. It's like it's something else. Something unknown. We have this big fear of unknown. Artificial is, not really well defined. It just means not real. Intelligence, wow, that's smart if something's intelligent. So are machines smart? I mean, maybe. So, we have a more palatable language today, machine learning, which instead of just artificial and unknown, we have defined it. It's a machine. Humans are better than machines, right? I mean, we all acknowledge that. We all think we are. So it makes us feel better to just say it's machine instead of artificial. And then instead of just intelligence, we say learning. If we can get a machine to learn, that's a great thing. Intelligence also includes the other half of knowledge base, which is knowledge. Starting with knowledge. So machines don't start, if it's learning, it doesn't start with knowledge. It learns knowledge, and then eventually we'll have it, but not from the beginning. It only learns what you teach it. So this is why machine learning is more the language these days than artificial